you go. Wonderful. Yeah, who's going to be talking about nuclear, which is a really fantastic follow-on to some of the prior discussions, particularly some of the questions from the earlier discussion. Please do put any questions in the chat, and that could be integrative questions from all three, questions to specific speakers. And I also invite the speakers to respond in the chat, and I will also open up in the discussion afterwards. Dr. Shirvan, please do go ahead.
Thank you, Professor Jordan. Today I'll talk about nuclear energy costs and innovations that matter. Just like with any academic studies, like to acknowledge the people who do the work, which the work is not possible, with students, postdocs, scientists, as well as the sponsors, the Department of Energy. In particular, with respect to the material I'll talk about today, three sponsors are definitely worth noting: Electric de France, Exelon, and Fortum are all energy utilities around the world. So in this presentation, I will first compare the existing nuclear technology to combined cycle natural gas, which is the dominant technology right now in the US. Then I will also argue that overregulation and the perception of nuclear safety has led to the uneconomical performance that the first speaker was talking about, and try to challenge the philosophy that has really led to these unattractive cost features. At the end, I'll end with a list of innovations that matter, from really drawn up from a view of a bottom-up view for different nuclear technologies. So today, nuclear energy, it comprised about 10% of the electricity production around the world, and fossil fuels, of course, continue to dominate the electricity sector. If you look at that 10%, it's divided into 30 plus countries across 440 plus reactors. And each of these reactors that generate this electricity, about 95% of them are more or less of same type of technology. They're cooled by water. So when fission really started, and really how it got to be that make up 10% of the world's electricity, we saw it as a step forward to energy density. So if you compare the nuclear fuel, which is the uranium 235 isotopes for all those reactors, it ends up having a 70,000 times higher energy per kilogram compared to natural gas. And this is not the theoretical. The theoretical value is on the order of 100 million, but this is the practical value we get from current reactors. This graph, of course, is on the log scale. If you compare it to methane, hydrogen, all the other energy sources on the linear scale, they don't even show up to the graph. And other forms of nuclear technology, like fast reactor technology that has been developed in the US, Japan, France, India, China, and other countries, Russia, actually allows you to go even much higher in these energy density. And if you compare it to other carbon-free energy sources, you just can see the energy density right away. Here's comparing to a solar thermal plant. Solar thermal plant have higher energy density than solar PV. And this is the Ivampa solar plant in the US. It has 400 megawatt electric power rating. And it's important always to note the capacity factor, because that capacity factor translates to generation, comparing to the couple of plants in California, in Diablo Canyon Station, which supplies 5 times more power at much higher capacity factor, and as such, it takes very, very little land. Now, unfortunately, these nuclear reactors in California are due to shut down because California has decided that it doesn't want to, have nuclear energy in its state, and of course, California imports nuclear energy from neighboring states. But that's the situation in some states in the U.S. and similarly across the world, including Germany. So that physics really should tell you that fission should dominate. We have such a great power density; it doesn't take that much space. So what's the issue here? Well, if I show you a nuclear power plant construction and put it next to a construction for a natural gas power plant, you'll see that you don't see too much of a difference, particularly on footprint or amount of steel and concrete that goes into the plant. So let's see which one is nuclear and which one natural gas. You can see the one in the right is actually the nuclear power plant. These are the two reactors that are currently being built in Georgia, and they're vastly overcost, and they're vastly the construction time is vastly overrun. And you can see when you compare it to a natural gas on a capital cost basis, there's just no comparison. Natural gas is almost factor 10 times cheaper in capital costs. So we'll have to see what is the driver behind this cost, and really the construction of these two plants in Georgia has led the current energy utilities in the U.S. towards more smaller plants because they just can't afford this over $10 billion and 10 years of time to wait for the power to come online. So when you look at the technology to kind of make sense of what happened to that great power energy density that I talked about, let's start with what the nuclear fuel looks like. So the nuclear fuel in all those reactors, more or less, it's a form of this pellet made out of uranium dioxide. It's about 1 centimeter in height and 1 centimeter in diameter. And each pellet can provide 200 gallons of oil, or equivalent to 20,000 cubic feet of natural gas. So the energy density still, physically is there. So what we do, we stack up these pellets in this nuclear fuel rod, which is encapsulated by a sealed metal layer. And then we take these rods and we put them in a square array, about 300 of them, and make a fuel assembly. And then we take these fuel assemblies and put them in a kind of a circular fashion. And we got about 200 of these in a reactor pressure vessel, which is another sealed barrier around the nuclear fuel. And this pressure vessel, you can see, it's on the order of 13 meters in height and 4 meters in diameter. And they, on average, these things can produce 3,500 megawatt of thermal energy. So the energy density continues to be more or less there. But when you look at where this reactor pressure vessel is in comparison to everything else, you see that's actually a small part of the whole nuclear power plant. The turbine island, which you need for any fossil plant or solar thermal plant to also generate electricity, you can see that the sheer size of it is pretty large. We also have other things here that I'll discuss. So right off the bat, we're using water, and when you mix high temperature water and radiation field, materials become a really big issue, and we really become limited to water at below its critical point, or water at below 400 C to use available mature materials, and that lower temperature really limits the efficiency of going from thermal to electricity to 33%, which becomes half of combined natural gas plants, which are able to go to higher temperatures and leverage more complex turbine building. So we lose about half of that energy density there. Then you look at, okay, why do you need all these rest of these structures? Well, nuclear is a very highly regulated industry, and there is some good reason for that. Is that there is a nuclear hazard which is special to nuclear power plants, and that hazard basically coming from the fission process, where the products of that fission continue to generate heat even after you shut down the fission reaction. And as such, you have to always circulate water and always try to cool this nuclear fuel to avoid it from becoming in any unsafe condition. And because of that, we have multiple safety systems, diversity, redundancy, and those defense and depth barriers that I touched on. And that, of course, comes with a cost. The other reason those plants were, the cost of those plants in Georgia are actually higher than the ones that are, very similar ones being built across the world, is that in the US, we just haven't built many plants. And regardless of technology, whether it's batteries, wind, solar, coal, natural gas, the first of a kind is always going to have some issues And those are really first of a kind type of projects. So that was the story of the capital cost. Let's look at the operation and maintenance cost. How does nuclear compare to combined natural gas? A typical nuclear power plant you'll see today has about 500 plus staff for a 1,000 megawatt electric plant. But similarly, equivalent power, if you look at a combined natural gas, it only has 40 staff. So let's look at why that is. If you look at from the operations and training team, the nuclear power plant has a lot more, 70 more people there. And one of the main reasons is really driven by strict training. This human to machine interface has been pointed out as a big safety impact area that we like to have multiple operators. And when you have multiple operators and you operate these plants 24/7, you need at least 5 shifts to support that. And then when you have 5 shifts, you at least need another backup to a shift. And when you have so many people, you also need a sizable training crew. And all these operators continue to go through testing that if one of them failed, then they're ineligible. So you also need backup to backup. So you really need a large operating crew. Now, thanks to just natural advances in digital control systems and understanding of that human and machine interface, there is, for newer reactors, particularly some of the ones realized around the world, the operating crew actually, there is a high potential to reduce it. And we do have, support of the nuclear regulator to reduce that. But at the end of the day, we're always going to be higher than the natural gas plant for the reason I mentioned. For loss prevention, this is a huge difference between nuclear and natural gas plants. We always have to hypothesize that a small army of people would invade the nuclear power plant and start sabotaging it, perhaps releasing radioactivity outside of the plant. And as such, in the US, we have on the order of 100 security forces. The other issue with this is, as highlighted in Fukushima, if there is radioactivity released during these unforeseen disasters, that can cost billions of dollars. So you need people to make sure that the plant integrity is always met. On the engineering side, this is really a function of the fact that a lot of these reactors, as it was pointed out in the first presentation, we haven't added great capacity of nuclear in recent years. And so a lot of these plants are old. And in the old days, just like in any industry, you always hire the local people to work at your plant. Now, as the days have gone by, we become more of a service industry. So you subcontract all that work. So there is really no reason for this engineering to be as simple as a natural gas. On the maintenance side, there is in a nuclear power plant the additional hazard of radiation. So you do need health physicists. So at the end of the day, we end up, for even next future nuclear generations, we're going to need at least 90 to 300 staff per plant. So it's going to be higher than a natural gas plant, but it's not going to be as high as current reactors. And that's the story of the O&M. So now let's look at the total costs, which comprise of the fixed O&M, the staffing, the capital costs, as well as the fuel. And here's where we definitely make a good win, because the fuel cost, due to that great energy density, is going to be a very small part of the overall cost. Versus the natural gas plant, the fuel cost is actually the majority of the cost. You should please pay attention that this proportional percentage is only applied to water-cooled reactors. Many of the advanced nuclear reactors for future, they actually exhibit a much higher fuel cost. At the same time, maybe their O&M and capital costs may be lower. So this is really a water-cooled specific representation. If you compare it to renewables, as our chair talked about that, now we can say the words competitive renewable energy. You can see actually solar PV has similar type of structure. A lot of capital costs, small O&M. But percentages are very deceiving when you compare the data. You have to really compare it on absolute scale. Unfortunately, there are not really great measures of comparing different energy sources on absolute scale because you're not really capturing all the impacts. But levelized cost of electricity is one that we can use. And here, if you look at the levelized cost of electricity for nuclear compared to gas and solar, you see roughly about a factor of 2 difference. Now, what the picture really tells you is that even if you do reduce the capital cost of nuclear, you have to always try to keep this O&M and variable costs low, because really it's an extremely competitive market in today's world. Now, great thing is for the United States, our existing reactors have already paid off their capital costs. So we are dealing with the fixed O&M and the fuel costs. So they do actually give us a very low price of electricity. And a lot of it, if you look at the studies, a lot of it, they can even go much lower, but a lot of it is through regulations, and which I'll point out some of them that are just simply not performance-based. All right, so a few slides for the existing fleet of reactors and how we can reduce their cost and continue to have them on the grid, because it's extremely important to keep them as a carbon-free energy source, particularly with the current climate change targets. And the two ways we can do that, and the industry has done, is through life extensions and power upgrades. Almost all the reactors have already extended their life to 60 years, and some of them are going to 80 years. And that doesn't require really too much of a capital expenditure to do that. Another way that they've been able to reduce costs, they've actually existing plants, even though we haven't built any new plants, we've added 8 gigawatt electric of nuclear power plants, or 200 million tons of CO2 savings, by just better understanding how the nuclear reactor works and really removing a lot of the overly conservative margins that were in place. These power upgrades are very cost effective. Their capital cost comes at $1,000 per kilowatt. So it's competitive with natural gas and much cheaper than any other carbon-free energy source you can think of. And of course, that's the capital cost. I've already discussed the O&M on fuel is already very low. So the question becomes, can we go further, particularly for this session on energy materials? And the answer is yes. So one of the limits that limits, the power of a water-cooled reactor is this phenomenon called critical heat flux, which tells you that determines the maximum amount of heat that water can remove from a surface. And according to our regulation, and this phenomenon actually happens in conventional steam generators and boilers in normal power plants. And our regulator actually tells us that we have to assume that the nuclear fuel will fail when it undergoes this type of event. And in order to really overcome this, we can add some more pumping power, but that's, adding more pumps from a design point of view becomes impractical. And really what in reality happens, you just have a temperature rise on that nuclear fuel cladding, and the question becomes, does the cladding that's sealing the nuclear fuel can survive after this event? And if you look at all the experiments that has been done inside the nuclear reactor, you can see that there has been zero failure when the nuclear fuel for testing condition has undergone this. So this is really equivalent to if you're filling your gas car, you're told to just fill it up to half, or you're told to go to a reduced speed limit on the road without really any justification that there's an issue with your power plant operation. And in fact, since the Fukushima disaster, industry has started a lot of research and development in more accident-tolerant fuel forms. One of them is shown here, applying an accident-tolerant coating on the nuclear fuel. And you can see when you expose it at these temperatures, the fuel rod actually maintains its structural integrity much better. And in fact, if you do the calculations, you see that you can survive on these conditions on the order of days, versus current fuel can only survive on the order of hours. So hopefully these innovations can really allow us to overcome these highly conservative margins. Now let's talk about the future of our industry. So I think all the studies that account for the fact that the renewables do provide this in reliability, and the world of 100% renewable requires a massive overcapacity in order to meet the generation needs, show that if you want to get there, maybe nuclear can definitely play a big role. But right now, where we're anywhere close to decarbonization, nuclear is just simply not cost competitive. but we have to start building them in order for us to have its role there when we need it for decarbonization scenario. So if you look at commercial viability of a nuclear power plant, there's two really sides of this. One is you have to meet your market cost target, and that goes back to your LCOE components. The other one is you have to minimize the risk and uncertainty because you don't want to go over your cost target and you don't want to be delayed. So one answer that, as I mentioned earlier, is a smaller plant. Smaller plant is physically a smaller project, so it has inherently less risk and uncertainty. However, when you go to a smaller plant, what you've done is you've lost economy of scale. Now you need more material per power produced, so now your cost is higher. The number of staffing does not scale linearly with it. You have same number of systems, so you will likely have similar number of staffing. And the fuel cost also actually slightly increases. So we really, again, we need innovations for a smaller plants to be economical, because smaller plants gives us only half of the picture if we just simply scale the existing technology down in power. So let's look at what our industry and we have done since then. One of the ideas has been to increase the power density, so increase the power for the same reactor building size in order to reduce the cost. And this is what the small plants have done. Existing reactors have this reactor pressure vessel that you've seen already. They're connected to these large steam generators. And now they've actually, since you need a smaller reactor pressure vessel, they've actually integrated the steam generator within the reactor pressure vessel. You've eliminated these piping, and so you've eliminated the possibility of having this large loss of coolant from these pipings, and then you can actually reduce the amount of volume you need in your containment area. Another way of looking at this is you have a smaller power rating. There's just physically less heat to remove, so you can greatly simplify the number of safety systems you need in order to remove that heat coming from byproducts of fission during shutdown. And that has been the philosophy by some of the industry vendors. There's been also a whole lot of other ideas that have been going around last 30, 40 years: digitalization, robotics, advanced manufacturing, standardization, going to higher temperature to improve that efficiency. And the question really becomes, how do you know which one is worthy to pursue, and does it actually apply to all technologies? So let's look at why those solutions were proposed. Those solutions were proposed when researchers and industry has looked at the cost breakdown on the existing reactors. And this is the cost breakdown of existing reactor. You can see that half of the cost is on the construction and the installation cost, and about 20% of the cost is equipment. The question becomes, is this really applicable to all energy sources, all nuclear technologies, or because if it's not, then you have to come up with different solutions to reduce the cost. And actually, even if you look at the water-cooled technology, you see a wide range of performance, and you see that really any type of cost-effective solution has to be technology dependent. What you see here is the experience in Japan with building advanced boiling water reactors at much lower cost than those plants in Georgia. And in fact, those as much faster as well, at 3 years versus 10 years plus. And those plants actually feature much more volume of concrete per megawatt energy than those Georgia plants. If you look at what's the most expensive form of nuclear technology that has been deployed in recent years, it is actually the factory produced floating small modular reactor by Russia, having almost $240 per megawatt hour, or 24 cents per kilowatt hour. So this right away tells you that you really need to understand the bottom-up view of nuclear costs. And this is what we've done. We've gathered over 1,400 plus cost data. We've done a lot of benchmarks with public and proprietary data. And right now our model includes all the near-term water-cooled SMRs, and in future we're expanding it to non-water-cooled technologies. And this really allows us to evaluate what each innovation does. Some of these innovations, like advanced construction, you can see makes no difference in overall overnight costs, versus some have much higher sensitivity. So let's look at one example of this. This is the work we've done looking at what happens when you adopt a compact steam generator for an SMR. Because before we used conventional shell and tube steam generator because of their safety profile. But now with a smaller reactor, we've actually eliminated all those safety concerns. So we looked at about 10 years ago on what's the feasibility of it. And now this technology actually at the brink of commercialization. A couple of industry entities have adopted it as a reference for the nuclear power plant. And what it does, it allows you to have the either same power rating for a much smaller building volumes or higher power rating for the same size of volume. And let's look at now what's that impact. Well, what that allows you to do is it allows you to take a small reactor from 170 megawatt electric all the way up to 300 megawatt electric while still meeting all the safety goals that you have. And this great power uprate allows you to massively reduce the cost of modular reactors. Because by going from a large reactor to a small reactor, you've lost economy of scale, so your cost will go up. And this allows you to really even become cheaper than a large reactor by really improving how much power you're extracting from the same volume. Now let's look at what, how are we able to achieve it? Well, if you have a higher power rating, particularly with these newer designs that are have much higher safety profile than most of the operating reactors, all their safety systems are gravity driven, so you don't need external form of electricity to cool them. We typically characterize their characteristic with a grace period. Basically, the time until the nuclear fuel can get to an unsafe condition if you lose everything at your disposal. And the current reactors around the world, they typically have 72 hours after the Fukushima accident. They've upgraded that to have this coping time at 72 hours. And SMRs tend to have it more. And really what becomes important is how much more do you want to have? And what we see is that if we have 7 days, so 3 times more than all the brand new reactors being online, is actually gives you that much higher power if you do it 2 weeks. So that tells you that there's got to be a limit of how safe you can be, because if you look at, again, the safety profile of nuclear versus other energy sources, we're really the only industry that really emphasizes to make it safer than even real estate or any form of other industry. And that really comes at cost. And if you look at the non-water cooled reactors and what they've done, they've actually targeted infinite grace time, and that again has translated to high cost. There's also, if you can push it further, again, going above that critical heat flux limit I mentioned, again, allows you to go further. Now I'll conclude the talk with some insights that challenges kind of the state of nuclear community. We see that if you actually use these forced circulation pumps, you can actually gain a lot more in power density than if you use natural circulation. And the natural circulation plants, which means gravity-driven plants, really were born out of the 1990s, where I think there was, again, the first speaker mentioned that 20 to 30 years ago or 40 years ago, nuclear cost was not an issue. And back then, really the issue was public acceptance. So we decided to go to this ultra safe type of designs, and that really has cost us in terms of our cost targets. And if you look at all these small water-cooled reactors today proposed by US vendors are natural circulation, and all the international water-cooled small modular reactors are all forced circulation. So you can see the difference in philosophy. The other thing, for advanced reactors, actually the cost of equipment and cost of material are actually a large portion of their cost. And we have to continue to look at advanced manufacturing technique and cheaper materials. And lastly, the move to modular construction really happened as we went to bigger and bigger plants. However, by going to a smaller plant, we actually end up reducing that amount of workers on site. So it is actually disincentivized for us to go to 2 modular because you're paying so much overhead on factory and engineering and design. So my top 3 innovations that matter really is going to more performance-based regulation and radiation protection rather than trying to minimize it as much as possible, because no other form of technology really goes by that metrics in terms of hazard management. Second thing is cost-effective manufacturing technology becomes very important. You can see in that same table, the Chinese power plants are coming at much lower cost than the US power plants. It's the same way of why we're taking a lot of the solar cells cost reduction coming from, again, countries that are able to manufacture more cheaply. And going to higher temperature, again, always going to improve your your efficiency. Particularly, combination of these factors are extremely important. But unfortunately, with nuclear, things that are even away from the nuclear island, like valves and pumps from the turbine island, it becomes restrictive for us to purchase them from countries like China and India, because it's going to go into the nuclear technology at the end. So we really have to level the playing fields and further innovate to reduce this cost. With that, I'll conclude my presentation. Thank you.
Okay. I just want to say thanks. This is actually so interesting to see the potential decreases in costs that might be on the horizon for a technology that has obviously more recently experienced some challenges. For that reason, there are some, I have some comments and questions, but I'm going to ignore my own comments and questions and go right to the ones that were in the chat. The first one, it's from Rob Hayes in North Carolina State. Feels that the life cycle material requirements per gigawatt hour from each energy source should be considered, as they will eventually have to replace themselves, given that most mining, milling, manufacturing is currently enabled with fossil fuels. Can we discuss the life cycle, full life cycle materials, so the energy amounts of concrete, steel from the various energy sources per gigawatt hour? That's the first question, Koroush.
Yeah, I'm actually gonna share my slide again. Actually, it's in my backup slide. The IPCC actually has a great plot looking at life cycle emissions, where those life cycle material goes into it. And they do a range based on the range of studies available in literature. And if you look at the average, including a range, you can see that nuclear shows up as one of the lowest in terms of any type of life cycle emission. So that's definitely a factor of why people are continue to be interested in nuclear.
That's right. Yeah. And I mean, as someone in this field, it's also, from some of the comments yesterday, important to note that that's very true for material inputs relative to anything that's combusting a fossil fuel for any of these technologies. So thanks for bringing this up. This work was done by NREL, I think, led by Garvin Heath, who's done some great work in the area. The next question is about, and please do, if anyone has any integrative questions, we have a few more minutes and I believe we can go afterwards into the break. But the next question is, does the cost for nuclear plants include decommissioning, waste removal, and storage costs? And I'm presuming, actually, this is a really interesting question. I would also, ask, hey, is that also long-term storage costs? Because obviously there's a bit of a question mark in terms of what's going to happen with the spent fuel.
Yeah. In all LCOE calculations for water-cooled reactors, there's a $1 per megawatt hour that's reserved for that cost, and that for decommissioning as well as waste disposal, and that amount of money has proven to be sufficient so far. Well, of course, there's uncertainty about US, which deep geological repository we're going to go to. Some other countries already have picked them. Some other countries have already built them. But for water-cooled reactors, we account for that cost based on experience. For other reactors, that's an important question because there's just unknowns, and sometimes they're not included. So it's a good point that really all technologies should include that cost in the LCOE projection.
And I could certainly ask a question, everyone. We're already up at the end of the time. Ju, what is your recommendation here? I'm sure that our speakers have
we can keep going. Now is the end of, so it's a free for all, so everybody can chime in and we can talk about all different 3 talks now together. So just keep going.
Okay, well, I would just, I'm just going to start and just encourage if anybody else has any questions. This is the big energy materials session. So I'm just going to ask a kind of big, broad question to everyone. Hey, given your talk and your focus, what do you see as the biggest thing that could really have an impact in the particular energy transition or technology that you're looking at in terms of moving towards the goal of this, the whole purpose of this conference, which is to meet Paris goals? And I'd love to hear your thoughts from each of you. And hopefully this will also provoke other questions from our attendees as well. So please, I don't know if maybe we could go in the order of the presentations.